Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this video we're going to look at atomic radii and the trends of how it changes both across a period and down a group in the periodic table. So what we mean by the atomic radii is the radius or the length between the central dense nucleus and the outermost electron of an atom. And what you can see here is we have a Bohr model of the atom, with each of these representing an energy shell. The first one being n equals 1, second n equals 2, and the third one in this case n equals 3. As stated before, the radius of the atomic nuclei is the distance between the central nucleus and the outermost electron, and so therefore the outermost energy shell. Now there are two factors that affect the distance here, which therefore means the atomic radius changes. And those two factors are, first of all, the nuclear charge, so the number of protons in the central nucleus, which increase the positivity of that central nucleus. The next thing to be aware of is the number of inner shells and the electrons which they hold. If we increase the inner shells, we increase something called shielding. And the shielding is the idea that if we have more inner shells and their electrons, then these inner shells reduce the attraction towards the positive nuclear charge and the outermost electron, because that inner positive charge is being shared out between more electrons on the way to that outermost electron, feeling that electrostatic pull. Now finally, if we increase the number of inner shells, then what we're also doing is increasing the distance between the positive nucleus and the outermost electron, and attraction drops off as distance increases. And so all of these three different factors of nuclear charge, shielding and distance can have an effect on the atomic radius, which is the length between here and here, the outermost. And it's really key to be aware of some key relationships. So as we increase the proton number and increase the nuclear charge, then we decrease the atomic radius because there's more of an electrostatic attraction. And also, as we increase the number of inner shells, we increase the shielding and increase the distance, which leads to an increase in the atomic radius. And so these are some key ideas that will be useful not only for explaining atomic radii in this video, but also ionization energy and how it changes in following videos. So now we're going to apply some of these ideas to two different situations when we go down a group, and we're going to be looking at group 1, so this part of the periodic table. And then what we're going to do is look across period 3. So we're looking across from sodium all the way through to argon across our periodic table. And what we're going to explain is how, when we go down a group or across a period, the atomic radius changes for the atoms involved. So focusing on going down a group, group 1, we've got lithium to sodium to potassium to rubidium to cesium. And in each of these cases, as we go down, the atomic number or the proton number increases. And you can see this alongside here. The first fact that we can explain is that as we go down in a group, we have an increasing proton number. And so this increasing proton number increases the nuclear charge within our atom. And we can see this in this really simplistic idea, but we've got one positive here and two positives here. So basically it's increasing each time. So obviously that will have an effect on the outermost electron being attracted to the positive nucleus, as it is more positive. Now the other important thing to note is that if we increase the proton number, we not only increase the number of protons, but we also increase the number of electrons. And you'll remember that from some basic chemistry from both GCSE and at the very beginning of A-level, because lithium, for example, has a proton number or atomic number of 3, and that tells you both the number of protons and the number of electrons in a neutral element. And in this case, for lithium, it means we have 3 protons and therefore 3 electrons. And so that means sodium has 11 electrons, potassium 19, rubidium 37, and cesium 55. Now, the important thing is where these electrons end up. And as we go from lithium to sodium to potassium to rubidium to cesium, we're entering new periods in the periodic table. So lithium is in period 2. And the period that you are in tells you the number of shells that you have. So lithium has 2 shells, the first shell having 2 electrons in, and the second shell having 1 electron in, making up the 3 altogether. Sodium is in period 3, and so has 3 shells. Potassium, period 4, 4 shells, rubidium 5 shells, and cesium, period 6, so has 6 shells. And so as we go down a group, we are increasing the number of electrons. They are entering different shells. So we have an increase in the number of inner shells. And this has 2 effects. If we increase the number of inner shells, you can quite clearly see from this sketch that the distance between the inner nucleus and the outermost electron increases. And also, the increased amount of inner shells means that our shielding also increases. And it's these 2 factors here of increased shielding and increased distance that we have an increase in the atomic radius. One, because the shielding means there's less attraction to the inner nucleus, and the distance obviously is quite easy to see how that affects the atomic radius. Now it's important to note, we started discussing earlier that we do increase the proton number, and so we increase the nuclear charge, and so the positive charge within the nucleus. And that would lead to a decrease in distance, because the outermost electron and the nucleus are more attracted together. But this whole column here is offset from the effects of this column here. So this argument, whilst it does happen, but its effects are less felt than this side here. And so overall, we have an increase in the atomic radius with this factor here being outweighed overall. Now we're going to focus our attention going across a period on the periodic table and looking at the effect that that has on the atomic radius. Before we go on to that, what I would like you to do right now is pause the video and see if you can come up with an explanation for why the atomic radius follows this trend as we go down a group. See if you can recall the exact concepts, and then go back and check your answer. So as we go across period 3 here, the proton number again does change. And so the first effect that we can use to explain is that we have an increased proton number, and so an increased nuclear charge. And with this increasing nuclear charge, then what we're going to have is more of an attraction between the positive nucleus and the outermost electron. And so this is going to reduce the distance between the two. Now, on the other hand, as we've stated before, if we increase the proton number as we go across this period, then we're also going to be increasing the electrons, because the proton number tells you not only the number of protons, but the number of electrons. But this time, something worth noting that was different to the group situation is that these protons are all entering the same shell because they're the same period. So sodium through to argon are period 3. So sodium through to argon all have 3 shells. And so whilst we're increasing the number of electrons, we're putting this in the same inner shells, and so shielding remains exactly the same, as does distance between the outermost electron and the nucleus, because there's no more shells to increase that distance. And I'm just using these symbols here to show that it's unchanged, because it's neither increased nor decreased. And so this column, these explanations that were really important for going down a group, this time this column has no effect on the distance. Whereas this column here, to do with nuclear charge, does have an effect, and it decreases the distance. So overall, we have a culmination of a decrease in the atomic radius as we go across a period. So it's really important that you learn the process for not only across the period, but down a group. In a minute, I'm going to wipe the slide clean, and then what I'm going to get you to do is pause the video and try and jot down exactly what the two explanations are for down a group and across a period. And then what I want you to do is give it a day or two, and then try to be able to explain both of these concepts again to someone else or on your own on a piece of paper. All of this is going to be really key because it will form the bedrock of explaining trends in the ionization energies across a period and down a group. Okay, so pause the video now and see if you can explain the trends in both these graphs. And then make sure that you go back through the video and check your answers to those explanations. So in this video, we've been able to describe and explain how atomic radii decreases across a period using the principles of shielding, nuclear charge, and distance. And then we've also been able to use those same principles to explain how atomic radii increases as we go down a group. If you found this video, be sure to like it. Be sure to subscribe to the channel so that you get updates as and when they come. And then importantly, use the ideas and concepts in this video in order to understand ionization energy, which can also be found in the playlist for periodicity at A-level chemistry.